Okay, so welcome to the second talk of BRAC. So I have a few announcements before that. We're gonna go for dinner after the talk, not right after, but we're gonna leave from IMPA at 5 o'clock and go to Restaurante Peixeiro in Rua Real Grandeza in Botafogo. So if you want to join us, you can come with us or join us there. Also, I forgot to mention in the first talk that those of you who are following online, you can make questions. You just unmute your microphone and you can make the question and we can hear you. Okay. So the second speaker today is my colleague, Olivier Martin from IMPA, and he's going to talk on isotrivial Lagrangian fibrations.
Thank you, Eduardo. So I'd like to thank the organizers for the occasion to speak. So I'll be talking about a project that I've been working on for over a year now with Yoonju Kim and Radu Laza. Radu's at Stony Brook, and Yoonju Kim I think he hadn't graduated yet when we started this project. So now he's a postdoc at Columbia. He did a year at Bonn, and now he's at Columbia. He's a student, was a student of Radu. So this is roughly the outline of the talk. I'll start by talking to you about elliptic K-tree surfaces, isotrivial elliptic K-trees, and then I'll move on to what are hyper-Kähler manifolds and some of the motivation for this work. And then I'll try to present 4 theorems. It's a little bit ambitious, so maybe if we don't have time, then I'm starting with the most exciting theorem, I think, and then we'll go down the line from there. Don't hesitate to ask questions during the talk. So we start with the definition of an elliptic fibration. So if you have a K-tree surface, an elliptic fibration is just a morphism with connected fibers, so a fibration to a smooth curve. Automatically, that smooth curve must be P1, because if it had higher genus, you could pull back holomorphic forms and get forms on your K-tree, which it doesn't have. And by Riemann-Roch, you see that the generic fiber, the smooth fiber, is going to be K-trivial. It's going to have a trivial canonical bundle, and so therefore it's going to have genus 1. So that's why it's called an elliptic fibration. An example of such a fibration is if you take a quartic surface. Smooth quartic surfaces in P3 are K-trees, and if that quartic contains a line, you can project from that line, and a priori that's just a rational map, but to a point that's on the line, you could associate the tangent plane at that point. That gives you an elliptic fibration. And if you want to convince yourself that it's an elliptic fibration, if you take a plane that contains this line, what is the fiber over this point? It's going to be the residual intersection of this plane. So the plane is going to intersect your quartic in this line along with a cubic curve. In general, this cubic curve is going to be smooth, so it's going to be a genus 1 curve. And whenever you have an elliptic K-tree surface, you get a moduli map. So to a point in the base that has a smooth fiber over it, you could look at the Jane variant of the smooth fiber. That's going to give you a map to A1, the coarse moduli space of genus 1 curves. And this map is isotrivial. The elliptic fibration is called isotrivial if this map is constant. So this amounts to saying that the smooth fibers are all isomorphic to one another. So here's an example of an isotrivial elliptic fibration. I could start with an abelian surface that has a surjective morphism to a genus 1 curve, and such that the fibers are also connected genus 1 curves. So for instance, a product of 2 elliptic curves would do the job, but you could have something that's not a product that still has such a map. And then you can construct what's called the Kummer surface associated to that abelian surface. You can quotient by the plus or minus 1 involution. This is going to have 16 ordinary double points that correspond to the 16 torsion points, 2 torsion points on your abelian surface. And if you blow those up, you're going to get a K-tree surface. And just as your abelian surface A had a map to E, the blow up is going to have a map to E, and this is going to give you a map from X to E mod plus or minus 1, which is just P1. And the generic fiber of this elliptic fibration is going to be F, so it's going to be isotrivial. So a natural question is, I just highlighted for you a construction of an elliptic K-tree surface. So one can ask, is this kind of a typical way that you write down an elliptic K-tree? And the answer is it kind of depends what you mean by typical. So if the fiber is generic, then that's the only way you can construct an elliptic K-tree surface. So if you have an isotrivial elliptic K-tree whose smooth fiber has a J invariant different from 0, 17, 28, then it's built exactly in the way that I just described for you. It has to be the Kummer of some abelian surface that's isogenous to a product, and the fibration arises by some map to a genus 1 curve. On the other hand, there are examples of more complicated elliptic fibrations. So you can find, if you look at a Kummer of an abelian variety isogenous to a product, these are going to come in 2-parameter families. You have 1 parameter for E, 1 parameter for the fiber F, right? So you can modify these 2 parameters. That gives you a 2-parameter family of such Kummers. But there are much larger parameter families of isotrivial elliptic K-trees. So from the point of view of moduli, if you're asking, can I find large families of isotrivial elliptic K-trees, turns out you can, but you're not going to be able to find them by the Kummer construction. So there are large families of isotrivial elliptic K-trees if you take the fiber to be quite special. So here's an example. If you take the fiber to have J invariant 1728, what that means is that it's an elliptic curve that has automorphism Z mod 6Z. So it's an elliptic curve with a lot of automorphisms. And you can take a cyclic degree 6 cover of P1, ramified at 12 points. And then when you look at C cross F and you look at a diagonal Z6 quotient, this is going to turn out to be birational to a K-tree. This is basically, if you want some statement about what the eigenspace for the zeta eigenspace for where zeta is a root of unity looks like. It turns out to be one-dimensional in this case. And so you're going to get something that's birational to a K-tree. And this is going to depend on 9 parameters because you're choosing 12 ramification points minus the automorphisms of P1. So in this way, you get a large family. And you can do the same thing if you look at elliptic curves that have J invariant 0. So we're going to call those Dilling-Mostow K-trees because they arise in some work of Dilling-Mostow on hypergeometric functions. So I'll talk, we'll have this dichotomy between, on the one hand, we have these Kummer-type isotrivial K-trees, and we're going to have these kind of more exotic Dilling-Mostow type. Yes? Yes. So there's so if you don't care about so if we assume that there's a section, then you can write down a complete list, and we do that in our paper that has yet to come out, but I think that's been known for quite a while. There's a paper of Moonen, which is called the Dilling-Mostow list, and something else. And he gives a list. It's not quite exhaustive. I think there's a couple of examples missing because he's not looking at exactly the same thing that we're looking at. But if you don't have a section, then you have some type of twist, right? You can kind of pass from. So it should be more or less it's exhaustive. Well, you have kind of a similar construction. If that J invariant 0, you get a Z mod 4Z automorphism, so you could do the same thing. But there's also more exotic things that. I don't know. I don't remember off the top of my head. It might be. I don't remember exactly off the top of my head. Okay, so let's move on to. So our main topic is going to be hyper-Kähler manifolds and Lagrangian fibrations. So hyper-Kähler manifolds are analogs of K-trees in higher dimension, and Lagrangian fibrations are going to be analog of elliptic fibrations. So what is a hyper-Kähler manifold? It's a simply connected compact Kähler manifold such that the space of holomorphic 2 forms is one-dimensional, and it's spanned by a nowhere degenerate form. So that's called often a holomorphic symplectic form. And so what does it mean to be non-degenerate? It means that when you take the top power of that 2 form, you're getting a nowhere vanishing section of your canonical bundle. So in particular, such varieties have a trivial canonical bundle. And there's, in some sense, one of the 3, there's this theorem of Bovil-Bogomolov that said that if you have a compact Kähler manifold with trivial canonical, there's an étale cover that splits as a product of complex tori, strict Calabi-Yau's, and hyper-Kähler. So they're kind of one of the 3 building blocks of compact Kähler manifolds with trivial canonical bundle. So let's give some examples of such varieties. So I told you there are generalizations of K-trees. So K-trees in particular are examples of hyper-Kählers. But more generally, if you take a K-tree surface and you look at the Hilbert scheme of endpoints on it, that turns out to be a hyper-Kähler manifold. And hyper-Kähler manifolds that are deformation equivalent to such, we're going to call it of K-tree type. There's another construction where instead of starting with a K-tree, you start with an abelian surface. And there's a construction that's kind of analogous to the construction of a Kummer, which is called a generalized Kummer construction. So you take the Hilbert scheme of n plus 1 point on your abelian surface, And this has a non-trivial Albanese map, which is basically a summation map. If you look at the fiber over 0, or equivalently, you look at a generic fiber or a smooth fiber of this fibration, this is going to be a generalized Kummer, which is written as cum n of A. And things that are deformation equivalent to that. So this is a hyper-Kähler. Things that are deformation equivalent to that are going to be called of Kummer n type. So both of these give infinite families starting from dimension 4. And dimension 2, well, Kummers are K-trees and K-trees are K-trees. So they kind of degenerate to being the same deformation type in dimension 2. But in all other dimensions, these give you different deformation types. And it turns out there are 2 more deformation types that are known that are called O'Grady 6 and O'Grady 10 that are constructed as some moduli of sheaves, some disingularization of some moduli of sheaves. I'm not going to go through that, but there's 2 more exotic deformation types. So a really important question is, is that it? Do we have any other deformation types? So this is really one of the big questions in the theory of compact hyper-Kähler manifolds. And another question is, do we know that in every dimension there are finitely many deformation types? So at the moment we don't know that, but it's expected that in every dimension there's finitely many deformation types. So for K-trees there's 1 deformation type. That's all that we know. Starting from hyper-Kähler fourfolds, we know 2 deformation types, but a priori there could be infinitely many. All right, so what are Lagrangian fibrations? As I told you, they're analogs of elliptic fibrations of K-tree surfaces. So a Lagrangian fibration is going to be a fibration, so a morphism with connected fiber, from a hyper-Kähler manifold to a variety such that the fibers, the smooth fibers, are Lagrangian submanifolds. So Lagrangian submanifold means that this holomorphic symplectic form restricts to 0, and it means that they're maximal dimensional such that it restricts to 0. So in particular, their dimension of the fiber is going to be half the dimension. The dimension of the base is also going to be half the dimension. And moreover, so since we have this holomorphic symplectic form, we can write down an isomorphism between the tangent bundle of the smooth fibers and the conormal bundle of the smooth fibers. But this is a fibration, so the conormal bundle, well, it's the dual of the normal bundle, which is trivial because it's a fibration, and so the tangent bundle as well is going to be trivial. And if you have a compact Kähler manifold with a trivial, that's an exercise. If you have a compact Kähler manifold with a trivial tangent bundle, then it has to be a complex torus because the Albanese map is unramified. And so the fibers are actually complex tori, and they turned out to be projective. They turned out to be abelian varieties. So really what you have is a fibration by abelian varieties that are half the dimension of the total space. And just as in the case of elliptic K-tree surfaces, you can ask, do these abelian varieties move in moduli, or are they all isomorphic? Are the smooth ones all isomorphic to one another? And if they don't change in moduli, then you see that it's isotrivial. So if all the smooth fibers are isomorphic to one another, then it's called isotrivial. All right, so here are some examples of Lagrangian fibrations. These are sort of 2 stupid examples, but part of this talk is going to be, okay, they're kind of silly examples, but there's a lot of, this exhausts a lot of isotrivial Lagrangian fibration, as we'll see in a little bit. So if I start with an elliptic K-tree surface, and I look at the Hilbert scheme of endpoints on an elliptic K-tree, this is going to come with a Lagrangian fibration. So you can look at the map from the Hilbert scheme of endpoints on the K-tree to the Hilbert scheme of endpoints on P1, which is just a symmetric product, which just gives you Pn. And this is going to turn out to be isotrivial if and only if the original fibration was isotrivial. Similarly, if you have an abelian surface and it has a morphism to an elliptic curve with a connected fiber of genus 1F, then you get a morphism from the Hilbert scheme of endpoints on A to the Hilbert scheme of endpoints on n+1 points on E. And the generalized Kummer, which was the fiber of the summation map, is going to map to the fiber of the summation map, which is just Pn. So in the same way you get Lagrangian fibrations, and this is a Lagrangian fibration, you can check that the fiber is just going to be f to the n in this case. The smooth fiber is just going to be a power of this elliptic curve f. So just notice that in both of these cases, you see that the fiber is isomorphic to a power of an elliptic curve. And we're going to come back to this later. So here are some of the questions that I'd like to address in this talk. So one is, what can one say about the fibers of an isotrivial Lagrangian fibration? So in the case of a K-tree, the fiber is a genus 1 curve, and every smooth genus 1 curve arises as one of the fibers. So there's really nothing much that one can say. But in higher dimension, then you can say, okay, does every abelian variety arise as the fiber of an isotrivial Lagrange fibration? it's going to turn out now that it's very much not the case. Another question we can ask is how typical are the two previous examples? So it's not really well-defined questions, but we'll have something to say about that. Another one is how sparse are isotrivial Lagrangian fibrations? In particular, if I give you an isotrivial Lagrangian fibration, can you deform it to a non-isotrivial Lagrangian fibration? The other question is also interesting. We don't, is there an isotrivial Lagrangian fibration in every deformation type? This is a very complicated question. We don't have anything to say about that. But going from isotrivial to non-isotrivial, we'll have something to say about that. Okay, so part of our motivation is this boundedness problem that I mentioned. Are there finitely many deformation types for hyper-Kähler manifolds in every dimension? And one of the ways to approach this is to try to use what's called the hyper-Kähler SYZ conjecture. So I'm not necessarily attributing it to Misha. It's treated in his paper. Who came up? Is it kind of a folklore conjecture, or is it your conjecture? Okay, so all right. So, but you can look at Misha's paper to get the statement is here. So the statement is that every hyper-Kähler manifold can be deformed into a hyper-Kähler manifold with a Lagrangian fibration. So if this is true, that this is really useful to get a boundedness statement, right? Because then it suffices to kind of understand Lagrangian fibrations. If you can bound the deformation types of Lagrangian fibrations, then you're good to go. And there's another theorem, which is sometimes called the Matsushita alternative, which was proved in full generality recently, building on work by Ben Bakker, building on work of Van Heemen and Voisin. And this Matsushita alternative says if you look at how the fibers of a Lagrangian fibration vary in moduli, you have this n-dimensional base, and they either don't vary at all. So either the fibration is isotrivial or they vary maximally in moduli. So if you want the moduli map is generically finite. You don't have any, you're not fibered by curves where the fiber is constant in moduli, for instance. So let's see how both of these things together could help us to get some type of boundedness statement. So suppose that I start with the Lagrangian, let's just treat the hyper-Kähler fourfold case. So suppose that I start with a Lagrangian fibration of a hyper-Kähler fourfold that has maximal variation. And let's assume that it has a rational section. Then from looking at, so to each point in the base, I can associate the fiber. Smooth fiber is going to be a 1D polarized abelian variety. So you get a moduli map that goes from the base of the Lagrangian fibration into a moduli space of abelian varieties. And since I started with something that had maximal variation, on the left I have a surface because it's the base of a Lagrangian fibration of a fourfold. So the fibers are two-dimensional, the base is two-dimensional. So this B is two-dimensional. And it's going to map to a surface in this moduli space, which is three-dimensional. Moduli space of abelian varieties is three-dimensional. And one thing that we know is that this B has to be uniruled. And moreover, it's known that this moduli space of 1D polarized abelian varieties is of general type if D is large enough. So what that says is that surface that we get, it cannot move. If you have a ruled surface in a threefold, it cannot move. You cannot deform it as a ruled surface because a threefold of general type is not uniruled. It's not covered by rational curve. So what that means is, if you have a family of Lagrangian fibrations, they all have the same fibers, which is kind of, we're not able to prove that that's not the case, but that seems completely nonsensical. That shouldn't happen. That would be really, really odd. So this should allow us to give some bound on the polarization D. And once you have a bound on the polarization D, getting a bound on the fibration type is probably not too bad. So it's conjectured to be Pn, and then there's all sorts of partial results. It's known to be P2 if you have a fourfold. Yeah, actually in this case it's known to be P2, so it's even better if you know. U and Oibrecht-Jou, I think, is the two papers. So maximal variation means that so you have this X, you have B, and inside of B you have I'm going to introduce it right away. B0 is going to be the complement of the discriminant locus. So that's the T's in B such that XT is smooth. And to this you can associate a moduli map which goes from B0 to this A2D. To a point T, you just associate the class of this abelian variety xt. Okay, you might protest. This is not really an abelian variety. This is an abelian torsor because it doesn't have necessarily an identity. But if you assume that it has a rational section, then you can associate the section image as being the identity. Does that make sense? Oh, sorry, I didn't. So you said maximal variation means that this map is generically finite. So actually, you have a two-parameter family. So a priori, you have a two-parameter family of abelian varieties. But as we said, it could be that the fibers don't vary at all in moduli. It could be that it's isotrivial. So maximum variation means that the fibers vary very maximally in moduli. So they span a two-dimensional subvariety of the moduli space. OK, so this is one of the motivations. Another motivation is just the search for new deformation types. So isotrivial Lagrangian fibrations are relatively simple, and they're kind of a good place to look for new deformation types. It's not unimaginable that there could be some deformation types where every Lagrangian fibration is like really exotic, and that it's kind of hard to attain, to kind of find a representative for this deformation family without having some type of Lagrangian. I mean, not every one of the members is going to have a Lagrangian fibrations, but it could be that you can find this deformation type by studying some very exotic Lagrangian fibration. We haven't found a new deformation type, but that was part of the motivation. OK, so let's set up the situation a little bit. We're looking at an isotrivial Lagrangian fibration. So it's a morphism from X to B. X is going to be 2n-dimensional. B is going to be n-dimensional. And we're going to write F for the fiber. And B0, as I wrote on the board, is the subset, the complement of the discriminant locus. So the locus in B over which you have a smooth fiber. And you have a monodromy representation, right? You have a local system of the first cohomology of the fiber. And this local system has a monodromy representation. And we're going to look at a base change, U to B0, a Galois base change, which trivializes this monodromy. So if you prefer, the kernel of this monodromy representation is a finite index subgroup, and so it corresponds to a Galois covering. And the image, in this case, the Galois group is going to be exactly the monodromy group, which is the image of this global monodromy representation. And so we write U for this cover, and we write Z, the map from Z to U is the base change of the original family. So Z to U is, again, an isotrivial fibration by abelian varieties that don't vary in moduli. And since G is a subgroup, so G is a subgroup of GL of H1, so G acts faithfully on the first cohomology of F. And there's actually a lot that's known about the restriction from the cohomology of the hyper-Kähler to the cohomology of the fiber. So there's this theorem of Chénier and Voisin that tells us that the image of this restriction is actually the algebra generated by an ample divisor on the fiber. So there's very few cohomology classes that come from restriction from the hyper-Kähler to the fiber. So in particular, in our case, that tells us that a G invariance of the cohomology of F, G acts on the cohomology of F. As I said, it's a subgroup of GL1, in particular of GL of H on the H1 of F. In particular, it's going to act on the whole cohomology group, cohomology ring of F. And this subalgebra, this polynomial algebra in the ample class is going to be exactly the G invariance. An upshot of that is that the first cohomology of F is actually simple as so this is a slightly technical business, but it's simple as a bimodule for the Galois group G and the Mumford-Tate group. So if you think of it, it has two structures. It's a Hodge structure, and it's a G representation. If you think of both structures at the same time, that's why it's a bimodule, then it's simple. So one way to see this is if it failed to be simple, it would be a direct sum of two Hodge structures. Both of these Hodge structures would be polarizable. So you could pick polarizations on both of these. Then you could take G to average these polarizations. And both of these polarizations would then be invariant. So you would have two non-proportional G invariant polarizations. And that would contradict the fact that you only have one, that the G invariant of, right, that would contradict the fact that the G invariant of the second cohomology is just Q. So a consequence of this fact is that, so when you have something that's simple as a bimodule and you restrict it to just one of the two structures, it's going to be isotypic. So it's going to be, it might not be irreducible anymore, but it's going to be a multiple of a simple thing. So if you look at it as a Hodge structure, H1 of FQ might not be a simple Hodge structure, but it's a multiple of a simple Hodge structure. So the consequence of that is that F is isogenous to a power of a simple abelian variety. So the fiber is not going to be arbitrary. It's either always going to be isogenous to a power of an abelian variety, right? So a priori it could be simple, but it's not going to be, if you look at a hyper-Kähler six-fold and you have an isotrivial Lagrangian fibration, the fiber is not going to be an simple abelian surface across an elliptic curve, for instance. And one more thing is that when you look at the representation on the holomorphic one forms, this is a simple representation, because when you look at the G invariance of H11, this is the same as taking, what is H11? It's H10 tensor H01. H01 is the conjugate of H10, which is the same thing as taking the dual when you're dealing with finite groups. So this is one-dimensional, but this is exactly the morphisms as G representations from B to V. So by Schur's lemma, you get that V as a simple representation. All right, so this gets us to our first and arguably main theorem, which is about the fiber of an isotrivial Lagrangian fibration. So I told you already, by this Shannon-Voisin business, we know that the fiber is somewhat special. It has to be isogenous to a power of a simple abelian variety. But that's not that special, right? It could be simple. A general abelian variety is simple. It's isogenous to a power of a simple abelian variety. So what we prove is quite a bit more. We prove that the smooth fiber of an isotrivial Lagrangian fibration is isogenous to a power of an elliptic curve. And that's really quite a strong statement, right? Because there's very few. You have a one-parameter family of elliptic curves, so you have a one-parameter family of possible fibers of isotrivial Lagrangian fibrations. So let me sketch for you how the proof goes. So kind of a key ingredient that I don't really want to get into too much, I'll just use this more or less as a black box, is that you have, in some sense, a second Lagrangian fibration. Whenever you start with one isotrivial Lagrangian fibration, you get a second one for free. And so the way that you can prove this is, remember we've base changed to trivialize monodromy, and the statement is that there's a G-equivalent isotrivial fibration to an abelian variety which is isogenous to the power, to the fiber of your original Lagrangian fibration. And if you look at the product of the map to U and the map to F bar, this is G equivalent étal and Galois. So when you pass to the G quotient, you're now getting a map from, it's not going to be a morphism, because when you take Z and you quotient by G, it's a subvariety of X. It's an open in X. It's not all of X. But you get a rational map from X to B prime, which is a quotient of an abelian variety. And this turns out to be another isotrivial Lagrangian fibration. It's not a true Lagrangian fibration because it's only a rational map. But still knowing that it's a rational map tells us a lot of information. And it's enough to get what we want in this case. So what do we do from this? So I'll just remind you this B prime is the base of this kind of second Lagrangian fibration, which is only a rational Lagrangian fibration. Okay, and this lemma is a little bit technical, but it's going to come in really, this is kind of the essence of the argument, so I do want to go through it quickly. And the point of this lemma is it comes basically for free if you throw a lot of things that we know about hyper-Kähler manifolds into the mix. So the base of this second Lagrangian fibration is Q Fano. So you know, if you're like me, maybe you don't like that too much, these kind of Q things. But so the point is that B prime is a quotient, and so the canonical divisor might not be a Cartier divisor. It might not be kind of a true line bundle, but a multiple of it as a veil divisor happens to be Cartier. And to say that it's Q Fano means that there's an integral, positive integral multiple of this canonical divisor, which is an anti-ample line bundle. So let's see how this goes. So first of all, the canonical bundle is going to be Q Cartier because it's a quotient of a smooth variety. So just the fact that it's a quotient tells you that it's going to be Q Cartier. This theorem of Shannon and Voisin tells us that this B prime has very little cohomology because the cohomology of B prime is the G invariance of the cohomology of B of the fiber because it's a quotient again. So you can see that it has very little cohomology. It has the same cohomology as Pn basically. And so in particular, what that tells us is that the Picard group pick 0 of that base has to be torsion. Next, you also know that it has to be simply connected because it's dominated by a hyper-Kähler. So you could resolve the indeterminacy by blowing up things in codimension 2. When you blow up things in codimension 2, you don't mess up the fundamental group. A hyper-Kähler is simply connected. So when you resolve the indeterminacy, you're dominated by something that's simply connected with connected fibers. And whenever that happens, the base also has to be simply connected. So, OK, what do we have? It's simply connected. Pick 0 is torsion. That actually tells us that pick 0 has to be trivial. Because if it had torsion in pick 0 can be used to find an étale cover. And if you had an étale cover, then you're not simply connected. Right? And so that tells you that pick 0 is trivial, which tells you that pick is just isomorphic to Z. And this is really all we need, because once pick is isomorphic to Z, you take a multiple of the canonical, it becomes a Cartier divisor, so it lives in pick now. And there's only 3 possibilities for something in Z, right? It cannot be too funky. It's either 0, positive, or negative. So it's either 0, ample, or anti-ample. So it's either Q, your thing is either kind of Q general type, Q Fano, or Q trivial. And it cannot be of Q general type or Q trivial because it's actually covered by rational curve. It's actually rationally connected by result of Q Sing-Lin. Whenever you're dominated by a hyper-Kähler, if you have a rational map from a hyper-Kähler that's dominant, then you're automatically going to be rationally connected. All right, so what is this business? How does knowing that this B prime is Q Fano give us anything about the fiber? Wrong side. So remember that B prime is a quotient of our abelian variety F bar, and F bar was isogenous to our F, right? So we really just need to show that F bar is isogenous to a power of an elliptic curve to know that F itself is isogenous to a power of an elliptic curve. So let's look at this quotient map and try to understand what happens at the level of the canonical bundle formula. So the canonical bundle formula tells us that the canonical bundle of F is the canonical the pullback of the canonical on B prime plus the ramification divisor. But the canonical bundle of F is trivial, and this thing is negative. The canonical bundle of B prime is anti-ample. So what that tells us is that the ramification cannot be trivial. So this quotient map has a non-trivial ramification. OK, so what? Well, if you have a quotient map, what is the ramification of the quotient maps? It's exactly the points that have a non-trivial stabilizer. Right? So what that means is that you have whole divisors along which you have a non-trivial stabilizer. So you have divisors that are stabilized by some non-trivial subgroup. And that's really a strong statement because the G action on the cohomology of F, I'll remind you, was fateful. So if you have, and if you look at the restriction map from the cohomology of F to the cohomology of D, so D is one of these divisors in the ramification locus that has a non-trivial stabilizer. Right, so D has a non-trivial stabilizer. Let's say it's stabilized by a little element G. So this restriction map from H1 of F bar to H1 of D cannot be injective because this little G acts trivially on H1 of D because it stabilizes D. It acts as the identity on D. So it acts trivially on the cohomology of D, but it didn't act trivially on the cohomology of H1 of F bar. It doesn't act trivially on H1 of F bar because the representation on H1 of F bar is fateful. So this map here, this restriction map, has to be non-trivial. Okay, so so what? Again, we have an abelian variety. We have a divisor, and the cohomology restricts has a kernel. When you restrict the cohomology, you have a kernel. Well, this is really, really rare. I mean, that's a really, really strong statement about that divisor in that abelian variety. There's only one possibility. The divisor has to be an abelian subvariety of codimension 1. Basically, the only case is your abelian variety is basically a product of an elliptic curve cross, up to isogeny, a product of an elliptic curve cross an abelian subvariety of dimension 1 less. And that divisor is that's abelian subvariety of codimension 1. So this is the lemma basically that we're using, which is, I mean, this is really simple. It could be kind of an exercise. So if you have an abelian variety and you have a divisor, such that the restriction from the cohomology of the abelian variety to the cohomology of the divisor is not injective, then D is a translative of an abelian subvariety of A. So automatically what we get in this way is that, remember, this F bar which is isogenous to F, contains an abelian subvariety of codimension 1, so it has an elliptic factor. So since F bar has an elliptic factor, F also has an elliptic factor because they're isogenous to one another. But F is isogenous to a power of a simple abelian variety. So if it's isogenous to a power of a simple abelian variety and you can find an elliptic curve in it, it has to be isogenous to the power of that elliptic curve precisely. So in this way, you're able to say that F is isogenous to a power of an elliptic curve. And so let's just prove this lemma real quickly. Why is it that if you have a divisor in an abelian variety and the cohomology restricts non-injectively, why do you get such a strong statement on what this divisor has to be? And it's really quite simple. So there's a kernel here, and this kernel corresponds to this kernel is a hot structure that's pulled back from a surjective morphism to an abelian variety. Basically because there's an equivalence between isogenies between abelian varieties and morphisms between polarized hot structures, contravariant equivalence of categories between these two things. And so what you can do is you can look at D, this divisor, look at its image, and you get from the fact that that the restriction of the cohomology so the restriction of the cohomology from, so here this K is the kernel. So if you go from H1 of B to H1 of A to H1 of D, this is the 0 map. And since this map over here is injective, you get that this restriction map must be 0. So what does that tell you? You get, basically what I've said is automatically you reduce yourself to a situation where you have another abelian variety, you have a subvariety of that abelian variety, and when you restrict from the first cohomology here to the first cohomology of that subvariety, you get the 0 map. The only way that can happen is if it's the inclusion of a point in an abelian variety. And so automatically from this, you get that this f of d has to be a point. And then for dimension reasons, you see that this surjection from A to B has to be a morphism to an elliptic curve. And then this d has to live in a fiber. So it's a codimension one translative and abelian subvariety. Yeah, I know it from, there's like there's much fancier incarnations of this, but like geometrically non-degenerate subvarieties. Zivran has done all this type of works on subvarieties where you don't get necessarily, here it's very easy because it's on H1. It couldn't be easier because it's just linear algebra basically, but yeah.
Yeah, but in these places there's always phrase in terms of the albanese.
Yeah. Okay, so this pretty much wraps up the proof of this one term. Okay, so if you were lost now, you can reintegrate, but maybe I'll lose you again in a second. So I'll do my best, but ask questions if you're confused. Okay, so the second theorem. So this ends kind of our first theorem. So our first theorem is about the fiber. The fiber is isogenous to a power of an elliptic curve. Okay, the second theorem sets up a dichotomy between two types of isotrivial Lagrangian fibrations. So whenever you have an isotrivial Lagrangian fibration, I'll just remind you, we have this setup. We trivialize a monodromy, and we look at the base change z to u. And in this situation, so we called u the intermediate trivialization, but you don't really need to worry about this. In these cases, there's two possibilities for the Kodaira dimension of this base u. Either the Kodaira dimension of u is equal to 0, and u is birational to an abelian variety, or the Kodaira dimension of u is n. So either u is of general type, or it's birational to an abelian variety. There's no intermediate behavior between the two. So in the case of Kumar, so you can think of that as being some type of Matsushita alternative, right? A lot of hyper-Kähler geometry is basically saying, things come in some type of discrete, they cannot range the whole thing, In the Matsushita alternative, either you're isotrivial or you have full variation. So this is a very similar statement to that. The Kodaira dimension cannot be 1 or 2. It has to be either 0 or all the way up to n. In the case of elliptic K-trees, if you're a Kumar K-tree, then you're automatically of type A. And if you're a Deligne-Mostow K-tree, so there's more exotic types of isotrivial elliptic K-trees, you might be either of type A or of type type B. So it's not quite the same thing as the distinction between Kummer K-tree and the Ling-Mostel, but it's a similar thing. Okay, so how do we prove this? So it basically just follows quite easily from the theorem of Kawamata. We're just kind of soup it up to an equivalent version of the theorem of Kawamata. So what does the theorem of Kawamata say? The theorem of Kawamata says if you have a surjective, if you have a generically finite, sorry, if you have a finite map from a normal variety Y to an abelian variety, there's a subvariety B of that abelian variety, such that when you look at the quotient from A to B, you can put it in a diagram like this, where the fiber of the map on the left is almost the same as the fiber of the map on the right. It's isogenous to the fiber of the map on the right. So in particular, the map on the left is a fibration by abelian varieties. And the map from Y to Y prime is, as I said, is generically an isotrivial fibration with fiber isogenous to B. And this map on the left is the Itaka fibration of Y prime. So in particular, Y prime, the dimension of Y prime is exactly the Kodaira dimension of this Y. Yes, of Y, sorry. So if the original map that we started with is G equivariant, then we can do all of this at G equivariantly. The B that we get is G equivariant. The map Y to Y prime that we get is G equivariant, and so on and so forth. So this is what we're going to use. So how does the proof go? So our U, we can put it in a smooth projective. We can find a smooth projective compactification for it. And I'll just remind for you that the So the partial trivialization was, okay, so it's just the trivialization of the monodromy. So this is just this thing that somehow we call it that in the paper because we have a full trivialization where we really want to trivialize it to be a trivial family with a section and so on. And somehow this stayed in these notes. But okay, so let's look at we let V be the representation on the holomorphic one-forms of the fiber. And you can check that V dual has multiplicity 1 in H10 of U bar. So there's two representations going on. There's the representation on the cohomology of the base and the representation on the cohomology of the fiber. And basically, they have to be dual to each other because you have a holomorphic symplectic form in degree 2. And so this has to come from exactly the pairing of one representation with the dual representation. In particular, you have one copy of V in the fiber. You cannot have 5 copies of V bar, V dual in the base. Otherwise, you would have 5 kind of invariant 2 forms. That's why you have exactly one copy of V dual in the base. However, this copy of V dual, in general, it's not going to be a Hodge structure. It's just a sub representation of complex vector space. So we can look at the smallest Hodge structure that contains this representation. And this Hodge structure is going to correspond to a map from U to an abelian variety. If you prefer, from the Albanese of U bar to an abelian variety, but in particular from U to an abelian variety. And this map has to be generically finite on its image, basically because the holomorphic symplectic form, when you raise it to the top power, it's a non-zero form. So you get a generically finite map from U to an abelian variety. This is not the setting of Kawamata, right? Kawamata, we have a finite map to an abelian variety, but we can just take the Stein factorization and make it finite. And the map from U bar to Y is going to be birational because it's a Stein factorization. So it's a Stein factorization of a generically finite map, and so it has to be birational. So we can just work with Y instead, basically. And what this equivariant Kawamata theorem says is that the Kodaira dimension of Y is the dimension of Y minus the dimension of B, because it's the dimension of this Y prime in the diagram. We have Y to Y prime, and the dimension of Y prime was the dimension of Y minus the dimension of B. And this is exactly N minus the dimension of B. But remember that A is a simple G abelian variety. It doesn't have any abelian subvarieties that are G invariant, because it's written as the smallest, its Hodge structure is the smallest Hodge structure that contains a given representation. So it's simple as a G abelian variety. And so in particular, if you have a G abelian subvariety, so a subvariety that's invariant under the G representation, either it's all of A or it's a point. There's no other alternative. And so this forces either the Kodaira dimension to be equal to 0 or the Kodaira dimension to be equal to n. If the Kodaira dimension is equal to 0, there's a theorem of Kawamata-Vivek that then says that the map from Y to A has to be an isogeny. So you get like that for free, that is birational to an abelian variety. Any questions about this? Okay, so now, so basically we've proven this type of alternative between two types of Lagrangian fibrations, isotrivial Lagrangian fibrations that we call type A and type B. And type A we should think of as, it's almost a quotient of a torus. So they're kind of tractable in some sense. Type B is potentially much more complicated. And we know that both of these types arise. You can write down examples of type A and examples of type B. An example of type B, for instance, would be if you look at one of these complicated isotrivial elliptic K-trees that I gave at the beginning, and you look at the Hilbert scheme of points on that, that would give you a type B fibration. Okay, so the third and probably last term I wanted to talk about is a type of classification for type A isotrivial Lagrangian fibrations. So it's a classification which is conditional on a conjecture, but it's a mostly believed conjecture, and it's a pretty standard conjecture in the field, which is the conjecture is if you have a Lagrangian fibration, isotrivial or not, then the base of that fibration should be Pn. So the theorem that we prove is that if you have an isotrivial Lagrangian fibration of type A, so this is the main assumption, this type A assumption, and if pi has a rational section, then and if moreover the conjecture holds, we just need it to hold for things that are birational to x, but let's just say that the conjecture holds, then pi is birational to either a K3n or a Kummer-n fibration. So in some sense, those are the only two. As far as birational geometry is concerned, those are the only two. Exactly. Yeah. Well, if you believe the conjecture, maybe that's the only thing. And the conjecture holds in dimension 4. So in particular, you can strike out in dimension 4. You can strike out the assumption of having this conjecture. And so again, in this case, the idea is that we have this z, which is obtained by base changing. And in this particular case, this z is a trivial family because you have a section and you've trivialized the monodromy. And so it's actually birational to u cross f. And since it's a type A fibration, u is birational to an abelian variety. So this z that we wrote down when the base change by trivializing monodromy is actually birational to an abelian variety. And this abelian variety comes with, it's a product, it comes with morphisms to f and f prime. F prime here is just an abelian variety that's birational to u. In particular, x is going to be birational to the quotient of an abelian variety by a finite group. And it turns out, so this is, this requires a little bit of work, but it turns out that this quotient admits a symplectic resolution. So there's a hyper-Kähler manifold, which is birational to x, and which is a resolution of this quotient. Now this hyper-Kähler manifold is equipped with two Lagrangian fibrations because it has these maps to these quotients of abelian varieties. If you believe this conjecture, well, or if you assume the conjecture rather, then both of these base spaces to which you map have to be Pn. And now you're in a good shape because it turns out that if you have an abelian variety with a finite group action whose quotient is Pn, it can only lie in a finite list. So there's a relatively small list that's been classified by, it looks like 4 authors, but it's 3 authors. Lucchini-Artek is one author, then the 2 others are another one. And it's not a paper by, maybe it's not a very good job that I did there, but it's not a paper, it's not a 3-author paper, it's like 3 or 4 2-author papers that have all manners of permutation of these 4 names, except if you have one of the 2 middle names, then you have the other one because they're the same author. So you can figure out how many papers are possible, and it's some subset of that. As I said, if you have a finite group acting faithfully on an abelian variety, and if it doesn't have translations, in our case we don't have translations because we act faithfully not just on A, we act faithfully on the cohomology of A as well. Translations act trivially on the cohomology. So we don't have translations. And in this case, if the quotient is Pn, so really it's not just the quotient being rational, right? You need it to be smooth. You need it to be smooth and to be Pn. So then you get actually a lot of information. So it's either a symmetric group acting on this kernel of the summation map, or a semi-direct product acting on a power. And there's one exceptional case in dimension 2, which is some group called the poly group acting on the square of an elliptic curve. And you can check that the first case, so remember that in our case, we have the same G acting on F and F prime. So that says that F, for instance, is a power of an elliptic curve. F prime is a power of an elliptic curve. Maybe you have the poly group acting on both of them, or you have symmetric group acting on both of them. But it's the same group, right? So it's really, you can just work out that the symmetric n+1 case is just a Kummer n fibration. The other one is a K-tree n fibration. And you can show that the poly group cannot give you a smooth hyper-Kähler manifold, because the singularity at the origin is just so bad that it doesn't have a symplectic resolution. So this guy you have to throw out. It doesn't show up. Okay, so maybe let me just, might as well finish. So there's one more, there's one more theorem that we prove, which is that isotrivial Lagrangian fibrations are relatively rare, right? So this was one of the things that we set out to do like 2 years ago or something when we started this project, was just, we want to apply it to be able to study deformation types. So we'd like to know that you can start from a Lagrangian fibration and deform it to a non-isotrivial Lagrangian fibration. And this is true. So if you have a Lagrangian fibration and the transcendental B2, so B2 is just the dimension of the second cohomology, transcendental B2 is the dimension of the transcendental H2, so you remove all the things that are algebraic. You remove all the Hodge classes. So if this is odd and greater than 3, then pi cannot be isotrivial. On the other hand, if B2 is bigger than 7, then a generic deformation of the Lagrangian fibration pi is not going to be isotrivial. So it's going to have, by this theorem of Backer, of Ben Backer, is going to have maximal variation. So on the relatively mild assumption, you can deform an isotrivial Lagrangian fibration to one that's not isotrivial. And the construction here is basically just Hodge theory, and it's more or less due to Moonen. So in this Dilling-Mostow list paper, he gives a construction for, so I don't know if you know this Kuga-Satake construction, but if I give you a Hodge structure of K-tree type T, you can always find a Hodge structure of weight 1 such that T is contained in W tensor W. And this is called the Kuga-Satake construction. And in general, this W you cannot take to be simple. But there are some cases in which you can take it to be simple. If the dimension of the transcendental Hodge structure is odd, then it has a real multiplication. The endomorphism algebra is going to be a totally real field. And in that case, you can assume that there is a simple Kuga-Satake partner, which is a simple weight 1 Hodge structure in which your T embeds, and such that if you have any 2 other Hodge structures of weight 1 in which T embeds, then they have to be isomorphic to this simple Kuga-Satake partner. And you can write down what the dimension of this simple Kuga-Satake partner is. It's either 2 to the L or 2 to the L minus 1, where the dimension of the transcendental Hodge structure is 2L plus 1. So what that tells you is if your Hodge structure, if you have a transcendental Hodge structure that has, for instance, dimension 4, then the simple Kuga-Satake factor is going to have dimension at least 2. So there's no way that your fiber could be a power isogenous to a power of an elliptic curve, because that elliptic curve would have to be a factor of that simple Kuga-Satake partner. And that can't be, because an elliptic curve cannot be a factor of a simple abelian surface. And on the other hand, if B2 is bigger than 7, then you can always deform that general Lagrangian fibration to one that has transcendental B2 equal to 5, and then this one is not isotrivial by this same statement. And so finally, there's some things that we're still trying to do. So there's something that holds for K-trees. Remember that one of the first things that I told you is if the fiber doesn't have G invariant 0 or 1728, then it has to be a Kummer. And we expect the same thing to be true for any isotrivial Lagrangian fibration. If the fiber is isogenous to a power of an elliptic curve which is not G invariant 0 or 1728, we think that it has to be of type A, and then it's either Kummer or Cum-N type. And we're almost there, but we're like still stuck. So this is one thing that we're trying to do. We're trying to see if O grady 6 and O grady 10 have isotrivial Lagrange fibrations. We have yet to be able to do that. Would be interested to know what happens if you don't have irrational sections. What can you say? Finally, there's interesting cases like the poly case, this kind of poly quotient case. We know that it can't arise when you have a rational section because, as I said, the singularities are too bad. But if you don't have a rational section, you can start doing a mix of translation and acting on the thing. And so you might hope that somehow the quotient has less bad singularities, and you might hope to be able to massage it into having things that have metasymplectic resolution, in which case probably it would give a new deformation type. But I mean, that's probably doesn't work. But you know, that's some of the hope. So that's it.
Okay, questions?
I have a question about Kodaira. So, can it have multiple fibers in the Lagrange vibration coming from Kodaira?
What do you mean?
So it might be that you have an orbital structure at the base, and you have like multiple fibers in the sense that you have a central fiber torus quotient by some finite group, and nearby fibers are just the same torus. This kind of multiple fibers, which you, I mean, for K3 there are no multiple fibers, but with
Okay.
period of surfaces. So the same might happen for Lagrangian vibrations. I don't know any examples. I think it was conjectured at least now.
I mean, this is quite a good question. I mean, this is another thing that we were trying to see, because in the K3 case, you use kind of the description of the local monodromy to know something about the singularities of the fiber, and then that kind of allows you to compactify it. Because, you know, part of our issues is we get this U, we get this Z, and then we don't know how to compactify it. So, you know, what we get is a birational statement. It could be that if you're careful and you really study kind of the local structure, then you can be able to compactify it. And I don't know if O'Grady could have.
Existence of rational functions is conditional on non-existence of multiple fibers.
Uh-huh.
Apparently, it's always true after some deformations preserving the monodromy, the fibers on the face.
Uh-huh. Okay. Sounds good.
More questions?
So what are your thoughts right now about the possibility of adding new deformation types with this isotrivial? Very unlikely, right? Or do you still have hope?
I think it's pretty unlikely in the case where the fiber doesn't have CM, or, you know, non-G-invariant 0 or 1728. And then in the other cases, I don't know. I mean, when you don't, like, if you don't have a section, you're not really looking at a torus quotient anymore, and then it's quite complicated. I don't really know if so. I'm kind of agnostic on the matter.
And the section were important in which statements? Can you recall? Did this zero and dichotomy, there was no section?
There was no section. So the section is only important in this classification statement that's the only one in which it shows up. And it shows up basically because you want to be able to say that this kind of once you trivialize monodromy, that you have like really a trivial family, that Z is a trivial family. It's a product, it's birational to a product of abelian varieties. Otherwise, you know, then you have to pass to a higher cover to get that section, right? You can always cover to get that section. So that's why we called it an intermediate trivialization, because it's not a true trivialization, because Z is not a trivial family. It's just a family with trivial monodromy. You can always base change more to get a section, but then this base is going to probably be of general type, and then you're screwed. So that's where it comes up, and that's why it's really tricky to kind of be able to say something when you don't have a section. So I mean, it could be that you can twist in some way, that there's some Tejchafarovich twist that resolve this kind of section/no section issue, but we haven't really been able to do that at the moment. You're saying if you have a smooth section, it becomes true, it becomes a real section, holomorphic after you trivialize monodromy. Okay.
Which preserves the base, preserves the fiber, preserves monodromy.
Uh-huh.
You said the topology, which is complicated.
Mm-hmm.
Okay, more questions there? Okay, so let's thank